Hey everyone. This lesson is on correlation and regression. Actually, regression is a huge field in mathematics because it helps to predict things. And a correlation, which is going to be our first part here, exists between two variables when the values of one variable are somehow associated with the values of the other. So picture someone who speeds a lot on the freeway and the number of speeding tickets that they have. That would constitute a correlation. The two numbers are connected. They have something to do with each other. Versus if someone says, I knocked on wood and did very well on an exam after that, there's no correlation there. And humans are really good at trying to make a correlation when there is none. So we need to use mathematics to figure out if there actually is. So when there is a correlation and we plot them on an XY table, this straight line that we get is called a linear correlation. And there are other types of correlations that can be made in mathematics, lots of them actually. But for this course, we're just going to stick with the linear correlation. And again, the linear correlation, measures the strength of the linear correlation between the paired quantitative x and y values. So to break that down, let's get some color here. Can you see that this kind of follows a straight line-ish? And what happens is we can use all these data points to come up with the slope and the y-intercept of this line. Our calculator will do that for us. Also, if you think back to algebra class, this is a positive slope. So r is positive in this case. Here we have a negative slope. You can see r is negative. And you can see there's, again, a line that, and in fact, these even seem more associative with that there. For this graph, there is no correlation at all. So r is 0 in this case. And in this one, there's a correlation, but it's not linear. This is a parabolic, actually. And so we would not say that there's a linear correlation here. So using some definitions here, r is what we're going to use for the linear correlation for the sample data. And as always, we're going to use a Greek letter r for the population, and that's called a rho. So rho is linear correlation coefficient for the population, which we don't know. We're going to have to use sample data to approximate that. And what I'm supposed to do, which I'm not going to do, is write down the formula for r here. It is terrifying looking. I'm happy to show it to you. Feel free to request it on the discussion board if you really want to see it. But I'm going to skip that for now. And we're going to move on to actually working this out. And so here, some properties of the linear correlation coefficient r is that it's always going to be between -1 and 1. And it measures the strength of the linear relationship. I'd like to kind of show you how this is going to work. So here's -1 and here's 1. This is r. And what's going to happen is we're going to end up with a boundary here. And in between here, if our r value falls into here, then there is no correlation. I should say linear correlation. And if it falls between our boundary, our critical values, and we'll learn how to get those in just a second, and 1 or -1, this means that there is a linear correlation. So we are going to talk about this example here. So here we have shoe print size and someone's height. And I'm going to assume that these are both in centimeters at this point. And is there a connection between a shoe size and a person's height? So it seems like there could be, or there should be, or there definitely is, or whatever. Again, if I wanted to do the formula, I would start filling in these boxes here, but we're not going to do that. We're going to use the calculator to do this. And you'll notice we have our alpha here is at 0.05. And in this case is 5. 1, 2, 3, 4, 5 paired sets. So again, view it like it's x and y. And so what we need to do first is come up with our null hypothesis. And this is that rho is equal to 0. This means, I'll write that down in a second. H sub 1 is that rho is not equal to 0. And this means no correlation versus a correlation, linear correlations. And what we will do is set up our boundaries. Now you see that n is 5 and we have alpha is 0.05. And what I'm going to do, again, this is -1 to 1. And we need to get our table. This is called a Pearson table. Pearson correlation coefficient R. And these are going to be our critical values. So we have alpha is 0.05, n is 5, and so there's my boundary, 0.878. Make sure you practice with this. 0.878. So 0.878, that one's negative, and this one is 0.878. That one's positive. And of course, in the middle, we have 0. Now, the closer to 1 or -1 that our R value is going to be means that there is a correlation. And here's how we do this on a calculator. I have already put in the values for list 1 and list 2. Here we are. That's this here. And so here's how we do this. After you put that in, you can pause the video and put those in. You go to Stat, Tests, and we're going to run way down towards the bottom. Linear regression t-test. You want to write that down. Now I have mine in list 1 and list 2. Not equal to 0. Rho is not equal to 0. And I'm just going to calculate R. And I've scrolled down a little bit. And here's R. So let's write this down. R is 0.591, it looks like. And that's going to be here. And this is the no correlation zone. Right, like we have up here. No correlation. So we would come to the conclusion, overall, that there is no correlation, no linear correlation between the two. Make sure you practice with the calculator. We have 2 more examples. Next one is here. Once again, what I'm going to do is write out here. And it looks like we have 1, 2, 3, 4, 5, 6, 7, 8. So n is 8 in this case. Our alpha is right here. So let's set up our boundaries first. So again, 0.05 and 8, 0.707. That's our threshold. And once again, from here to here, there is no correlation. Otherwise, there is a correlation. So, our null hypothesis is that rho is equal to 0. We're assuming there is no correlation. And rho is not equal to 0. So, once again, I have put the numbers in already for L3 and L4. So this is to see if there's a correlation between PSAT scores and SAT scores. So once again, I'm going to go to Stat, Tests. I like going up because it takes me to the bottom. And there we have our linear regression t-test. And now I'm now if you notice, list 1, list 2, list 3, list 4, and so on are there. So I'm going to swap out list 3 and list 4. And calculate. And there's my R. And you'll note that I am here again. In the no correlation zone. No correlation. Last up, we have one more. This is the court income and justice salary. Excuse me, I have a small cough. And here's our alpha. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like n equals 9 in this case. And so let's draw percent a little bit. And we'll find our threshold. So once again, alpha is 0.05 and is 9 in this case. So here we have 0.666. Once again, this is the no correlation zone. And this is the correlation zone. Once again, I have preloaded these numbers into here. And mine are under L5 and L6. You can see 65 and 30 and so on. So once again, I'm going to run stat tests, linear regression t-test. And before I do that, I need to state my null hypothesis. L5, L6. You, of course, can just do L1 and L2 each time. You just have to enter them all in. Calculate. And there's R. Look at that. Now it looks like we're in the correlation zone. So, there is sufficient evidence to support the claim that there is a linear correlation between court income and justice salary. Make sure you practice these, especially with the calculator, but that's what we're looking for.